This video develops a Python script to simulate random walks with memory that permit intermittent transport. This sounds complicated, but is actually a modification of the elephant random walk which we covered in a previous video. Please watch the previous video first if you are new to these types of stochastic processes. The video refers to Kumar, Harbola and Lindenberg's 2010 model published in Physical Review E. This is an extension of the random walk with memory based on Schütz and Trimper's paper. There is at the core of it a stochastic evolution equation xt plus 1 is equal to xt plus sigma t plus 1, where sigma t plus 1 is a random variable. This is a one-dimensional random walk where x could refer to a position or maybe a share price. The random variable sigma t plus 1 takes 3 values, so that's the innovation compared to the elephant random walk model. So we include the 0 in this case, which means it's an intermittent transport, so basically nothing is changing. Now by including this option, the option that the system is at rest, many interesting features can be obtained. The history of realizations of this random variable is again captured in this tuple or list. So basically all past realizations are covered in the history. Again, initial conditions apply, so initially we are maybe at 0, but we can modify this. And there is no prior history for selecting the first random variable. So what we do is we move to the right with probability s and to the left with probability 1 minus s. Note that I modified the notation in line with the paper. Once time progresses, a history emerges and we select a time k at random based on all the previous points in time. This is exactly in line with the elephant random walk. After selecting time k, we take the random variable using the following process. Sigma t plus 1 is equal to sigma k with probability p, so that is persistence, and minus sigma k with probability q. And there is a probability r, which is equal to 1 minus p minus q, where the position remains unchanged. So that's the innovation. And the interesting aspect is just by adding this third option, you get a very rich possibility in terms of phenomena that can be captured using this model. Let's move to Python, where we just need to modify our previous script. So most of the initial parameters are very similar. The difference is here this rest probability. And I modified a bit the notation in line with the academic paper. So the first move now refers to a probability s. We have persistence, we have change, and we have rest. And then we go into the stochastic evolution equation. And that's exactly the same process as before. The first step selection is exactly the same. And then we have now the modified if, elif, else statement. So that's the main difference compared to the elephant random walk. Let's look at this a bit more carefully. So again, we have here a random array. In this case, I now named it W in line with the paper because R is used for this rest period. And in this particular case, if it is persistent, you take the same value from the previous realization. If it is not persistent, you take the minus sigma k. And finally, if all else applies, you take nothing, it just doesn't move at all, and you assign it a 0. So note here this if, elif, else sequence. So we check first this condition. If this condition is not true, we move to the next one. Yeah, so this explains the changes in our boundaries. And again, we append the history and we update our position. Let me just run this. We can start with maybe 50-50 values. So in this case, there is no rest period. So you should not have any intermittent transport in this case. And you see it looks just like a random walk. Well, it, as a matter of fact, kind of is. And now we could modify this a bit. We can increase the persistence a little bit. And we still basically do the same as we have done for the elephant random walk. And now it looks a bit more persistent, and we can modify this further. And you will end up now with quite a drifty random walk. We see that here, so persistence is high, but you don't see any kind of steady resting period. Now once you start modifying this, maybe we go down here to 60%, and you have now a remaining probability of no change, things will change. And you see that now you have these periods where there is no change in the position. Now this actually can be a useful model to understand high frequency data in financial markets, because in these circumstances you might have no change to a value. So that might be an interesting way of modeling it. So that's all for this video. I hope you enjoyed that. As always, give it a like, share, spread the joy of data analysis. All the codes, everything is on GitHub. If there are any questions, any issues, please leave a comment. And I'll see you in the next one.